Hello everyone, I am Harika Shinde from Institute of Aeronautical Engineering and I am from Computer Science and Engineering branch. Today I am here to share and present my AAT Tech Talk video of a course Database Management System. My topic is irregular, indeterminate, repeated facts in temporal relational database. Let's begin. Introduction. Time is pervasive of our way of dealing. As a consequence, time is often modeled in a databases. The scientific community agrees that time has a special status with respect to the other data, so that its treatments within a relational database context requires dedicated techniques. A flitter form of dedicated approach have been developed in an area of temporal relational database example, and different approaches have been proposed for supporting efficient access to temporal data and improving the effectiveness of information retrieval. Most TDB approaches focus on individual occurrence of facts whose time of occurrence is exactly known. Hill and Clifford distinguished among strongly periodic events occurring at equally distant intervals of a time, nearby periodic events occurring at regular intervals of a time, but not necessarily at equally distant intervals, intermittent events which occur repeatedly in time but without any regularity. Example, a man visiting a pub periodically, meaning that visits can be quite irregular, while several approaches include Hill to Zihilin and Clifford's one. Consider the first two classes above the third class has been, to the best of our knowledge, neglected by the TDB literature. Of course, if a fact or event repeats at irregular times, but each time is exactly known, it can be easily managed as a set of timestamp tuples. However, in many cases, only the span of a time frame time henceforth January 2015, containing all repetitions and the number henceforth cardinality 5 in example 1. Of such repetition is available, such as example 1 in January 2015, John attended 5 times the meeting of the boy bioinformatics project. In many cases, as in the above example, the exact time of facts of the given DDB granularity is not known and can only be approximated, so that temporal indeterminacy has to be faced. Temporal indeterminacy is so important that support for temporal indeterminacy was already one of the 8 explicit goals of the data types in TSQLT consensus approach. In effect, temporal indeterminacy has various possible sources, including scale, dating techniques, future planning, unknown or imprecise event times, clock measurements. Despite the diffusion of the phenomenon, dealing with irregular repeated facts or events in a frame time is, to best of our knowledge, an entirely new goal in TDBs. Coping with it requires the joint treatment of two phenomena, the cardinality of irregular repetitions and temporal indeterminacy. Since only the frame time and not exact the time of each occurrence is known up to now, only few TDB approaches have been face temporal indeterminacy, and none of them copes with cardinalities. Indeed, in section 2, we show that coping with cardinalities is a challenging problem. They must be an explicit part of a data model and algebra. Their treatment cannot be delegated to users and involves an in-depth extension of current algebra. Main problem and the solutions. We aim at identifying a data module and relational algebraic operators to cope with the irregular indeterminate repetitions in TDBs. The data module must be closed with respect to the algebraic operators to query it, so that the results of the application of such operator must still be expressible in our data model. Such a goal leads to important implications about our data model. We proceed incrementally. First, we focus on exact cardinality and convex frame time, and then we generalize. Two different problems have to be faced to cope up with the cases, like repetition of a fact and temporal indeterminacy. As regard repetitions, we could allow for duplicates. Several representing occurrence of value equivalent facts holding at the same frame time could be inserted in the same relation. However, the adoption of a duplicate has several disadvantages. Example, as regards space, and cannot be generalized to the case in which the exact number of repetition is unknown. As in example 2, we thus propose a compact solution where numeric attributes are used to represent the number of repetitions of a fact in a frame time. Here it is a figure showing different scenarios or a Q1 section. Scenario A and C shows two extreme situation. In A, intersection is empty, that is cardinality in 0, while in C, the cardinality of the intersection is maximum, possible between 5 and 3 intervals. Next, however, we want that our data module is our expressive enough to model the results of a relational algebraic operations. The generalization to model not just a fixed cardinality but a minimum and a maximum bound of it. It is a natural way to achieve such a goal. A sound generalization required to cope with complex cases such as example 2 regards the fact that in our approach the frame time may be a non-convex period of a time. For instance, the working days of January 2015 cover the time intervals. It is worth noticing that the cases in which there is just one repetition or the exact number of repetition of events is known can be easily modeled and constitute specific cases of a generalized model in which the minimum and maximum cardinalities are set to the value 1 or set to be the equal respectively. Indeed, the example in figure 1 demonstrates that even in case the exact input cardinalities are known, the cardinalities obtained after the application of a relational operators may only be bounded by a minimum and a maximum value. In particular, temporal intersection and thus Cartesian products always produce a lower bound of 0 regardless of the initial values. We ground our approach on such a consensus background, extending the algebraic operators to cope with the new attributes in the definition. Definition 2. We use the superscript IR, that is irregular repeated, for our operators, while union, intersection, and minus denote standard state operators. For the sake of brevity, we preliminarily define the set VEINT of f, s of all the tuples in the relation S that are value equivalent to a tuple f, that is that are equal to f as regards the values of non-temporal attributes. Second, and whose frame time intersects with f's frame time. Definition 1. In the following example, x stands for all x such that definition 1 sets a value of equivalent tuples given two relations R and S defined over the schema R is equals to A1 to AN of N, M, and FT, and a tuple F is equals to less than or equal to V by N1, M1, T1 belongs to R. We define V int of f comma s equals to f map f dash by f dash belongs to f dash a equals to f of a as the set of all and only tuples of f dash in S that are value equivalent to f and the temporally intersects f. Here it is a figure 2 which shows the differences. The yellow diagram shows the differences between red intervals and the blue intervals. Figure shows an example of a maximum cardinality. Now, our Cartesian products operate the intersection between frame times. The minimum cardinality is 0, since it may always be case that valid times of repetitions do not intersect with each other. Maximum cardinality is a sum of the two input maximum cardinalities minus 1. Reducibility properties of the algebra. Reducibility is fundamental for TDB approach. To grant the semantics of new operators which extend simpler operators to cope with new phenomena. In general, given any two relational model and algebra x and y, the reducibility of x to y is proved by introducing a reduction operator r and by proving that indicating OPX operator x and operator y to corresponding operators in x and y and are a relation in x. The following holds the analog hold for a binary operators. Relation operator x of r equals to operator by r of r. Interplay with other temporal algebra. Besides relational storing, irregular repetition, IR, that is irregular repetition, a database can consist also of other types of temporal relations. Thus, it is important to study whether an algebraic query can operate on such different types of relations. Properties 1 and above 3 three properties 1 and 3 above are very important to this respect. Given property 1, an IPE relation can be extended to become an IR1, that is irregular repetition 1, so that IR operators can be applied on it and primitive IR relations. In such a way, a comprehensive temporal database consisting of IT, IR, and periodic relations can be managed in an integrated way by temporal algebraic operators. Thank you. This was my AAT Tech Talk video of a course database and management system. Thank you.